In today's functional analysis class, we are going to discuss bounded inverse theorem. So first we state the theorem. It is theorem 11.1 in your text. So theorem, let x and y be Banach spaces. Let f belongs to BL of xy be bijective. Then bounded inverse theorem says that then f inverse belongs to BL of xy. Now we write the proof. So first we prove that f inverse is linear. So proof, let f belongs to BL of xy be bijective. Let f inverse from y to x be defined by f inverse f of x equal to x for all x in x. Then for x1, x2 in x and k1, k2 belongs to k, f inverse of k1 f of x1 plus k2 f of x2, that is equal to f inverse of, f is linear, so f of k1 x1 plus k2 x2. So by the definition of f inverse, this is equal to k1 x1 plus k2 x2. So this is equal to, x1 is f inverse f of x. So this is equal to k1 into f inverse of f of x1 plus k2 into f inverse of f of x2. So this implies f inverse is linear. Since f is continuous, it is closed. Hence, f inverse is closed. You can prove that f inverse is closed. You let yn converges to y and f inverse of yn converges to x in x. Let xn equal to f inverse of yn. We have xn converges to x since f inverse of yn converges to x. That is, xn converges to x in x and f of xn is actually equal to yn. This converges to y in y. Now since f is closed, xn converges to x and f of xn converges to y implies y equal to f of x. So this implies x is equal to f inverse of y. So therefore f inverse is closed. Our assumption was that yn converges to y and f inverse of yn converges to x. So from that we are getting x is equal to f inverse of y. Therefore f inverse is closed. That is, x and y are Banach spaces and f inverse from y to x is a closed linear map. Therefore, by closed graph theorem, f inverse is continuous. That is, f inverse is a linear and continuous. Therefore, f inverse belongs to BL of xy. F inverse belongs to BL of xy. This proves bounded inverse theorem. Note, we have the inverse of a bijective linear map from a linear space to a linear space is linear. And inverse of a bijective closed map from a metric space to a metric space is closed. Bounded inverse theorem shows that inverse of a bijective linear continuous map from a Banach space to a Banach space is linear and continuous. Now we write a remark. The bounded inverse theorem does not hold for non-complete normed spaces. For example, you let x is equal to c naught naught with one norm and y equal to c naught naught with subnorm. Then, if you define f from x to y by f of x is equal to x for all x in x, then f is bijective, linear and continuous, but f inverse is not continuous, since for xn equal to 1 1 etc 1 0 0 etc, where 1 occurs in the first n positions, we have subnorm of xn is 1. You know, it is the maximum supremum of modulus of 1 modulus of 0, so that is 1, and a norm of f inverse of xn, that is equal to 1 norm of xn. You know, it is a modulus of 1 plus modulus of 1 plus etc plus modulus of 1 plus 0 plus 0 etc. So this is n, 1 plus etc 1 n times. This is equal to n. This is true for n equal to 1, 2 etc. So f inverse is not continuous. Now we write some applications of bounded inverse theorem. First application, let x and y be Banach spaces and f be injective continuous linear map. From x into y. If f inverse from y to x is known to be discontinuous, then f cannot be surjective by bounded inverse theorem. That is, there exists some y in y such that the operator equation f of x equal to y has no solutions in x. So this is one application in operator equations. Second application. On the other hand, if f is known to be surjective, then f inverse is continuous. F inverse is continuous by bounded inverse theorem. That is, the solution of the operator equation f of x equal to y depends continuously on y. That's all for today. Have a nice day.